Hello and welcome back to the last lecture we're going to record for this class. And this is going to be, this is unnumbered, even though it's got a number, but it's the second unnumbered, so it doesn't count. This is a lecture that's not a required lecture. It's one of the two optional lectures for the last meeting of the course. And what we're going to look at in this lecture is an application of the cold plasma wave theory. And that application is more specifically to what is called lower, let's put a dash, lower hybrid current drive, which is often indicated with just with the initials. In this is America, what did you expect? The interest on this wave, the lower hybrid wave, and its use for driving current refers in particular to tokamaks. This is the main candidate for driving current into tokamak reactors if current drive system is needed, which may or may not be the case, but that's not something I'll get into in here. Okay, so what we're going to do is briefly touch on some of the theory of LHCD. One piece that we cannot discuss is the energy absorption by the plasma that leads to the actual transformation from an electromagnetic wave into a current that flows in the plasma. And the reason why we can't do it is that discussion, that piece of the story requires the use of Landau damping, which is a kinetic effect, which, strictly speaking, you can actually derive without using kinetic theory. But since we have not discussed it in class, I'm not going to use it. So I'm going to just leave you with that part of the story and ask you to take on faith the fact that energy actually gets deposited in the plasma and turns into an electrical current. The model we're going to use, as I said, is the cold plasma model, and we're going to use the two-fluid version. So this is going to be all we need to capture quite a bit of the physics, and chances are to make this fit in a reasonable amount of time. I'm actually not going to tell you about all the wonderful things that we can figure out. Now, I would recommend, if you're not fully remembering and on top of the discussion of waves and the treatment of waves using the dielectric tensor and the conductivity tensor that we've had in the previous lectures, to go review them. But our starting point is that formalism, again, including two fluids. And among other things, we've seen the presence of cutoffs and resonances. We've discussed what they mean. But one thing we have not looked at, because it is, in fact, kinetic piece of the physics, is what is I'm going to just call wave-particle interactions. Interactions that I may have a chance to spell correctly. And this is the part we're not going to discuss in detail, but I'm still going to tell you something about it. Let's say for energy transformation. Into current. Okay, so that's going to be our starting point, and let's get to it. Now, the key interaction that we're interested in, that is relevant for energy absorption from of the plasma from the wave, is what is called a wave particle resonance. We are not going to get into any details, but the condition for wave particle resonance is that the frequency of the wave must be equal to K parallel V parallel plus L omega cyclotron, where L is an integer number. I don't know what the current convention is about what the set of integer number includes. So L could be 0, 1, 2, and so on. In particular, this happens at the L equal 0 resonance, which is what is called the Landau damping. That's particularly important for lower hybrid current drive. The L equal 1 and L equal 2 resonances are important for electron cyclotron heating and ion cyclotron heating. And there are differences. We're not going to get into any of that. It's not something that is relevant to us. Okay, now we already know about wave resonances, and therefore you may wonder, why doesn't the energy transfer happen at wave resonances? Well, the reason is that those resonances, the fluid model is inadequate. It doesn't really give us enough information about the physics. And in fact, what happens at wave resonance is not an energy transfer, but a mode conversion. In other words, the energy of the wave does not get transferred to the plasma there. That's the part that's interesting to us. Mode conversion means that the the wave jumps to the solution that we have to look at, jumps to a different branch of the dispersion relation. Remember, dispersion relation is going to have some type of equation that's going to be depending on how we write it, and that may change the variable, but since we're in a three-dimensional system, it's most likely going to be a three-dimensional, a third order equation for the omega or n, and your variable may be n parallel per with all the complications that can occur in looking at our dispersion relation. And at resonances, the wave moves from one solution to another. That's what mode conversion is. And one thing you may have noticed is that I'm discussing way the sorry. Wave will encounter resonances, and I've not said anything about cutoffs, but we already know about them. So what I'm actually assuming is that the characteristics of the plasma are changing as the wave propagates, which is in contrast with what we assumed when we derived the cold plasma dispersion relations. Really, what happens is that the conditions in the plasma are changing slowly with respect to the wavelength of the wave, and therefore, in solving the dispersion relation, we can assume them constant, but then we can change. We'll look at what happens for different values of those constants. That's the approach that's letting us learn things about the wave using this model. Okay, then now what we can look at in detail, just using the fluid model, is I'll leave you hanging for a moment. We're going to look at accessibility. By accessibility, I mean the answer to the question, can the wave get to the point in the plasma where I want it to go? The idea is I'm going to use this wave to drive electrical current in my plasma. I know what type of current profile I want for whatever reason, I just know. And I have to see, can I make this current profile in my plasma? Well, if the wave cannot access the region of the plasma where I want the current to be, then that's not going to work. The wave is going to be able to reach the region of the plasma that I want is that it cannot encounter either resonances or cutoffs between the point where the wave gets to the plasma and the point where I want it to be deposited. And without getting into too much detail, typically, remember we're talking about tokamaks, the waves will be launched, well, from the edge of the plasma, where you can put an antenna to direct the wave to enter the plasma, but because of the geometry, the toroidal geometry of the system, most likely that's going to be in the outward side of the plasma where the toroidal field is lower. So that's going to be the point where I'm going to have the space to put my antenna, and that's where going to be where my propagation into the plasma begins. I'm just going to remind you, just in case, and let me do it this way. If we're looking at wave resonances and cutoffs, a cutoff is the condition for a cutoff is that the perpendicular wave number must go to 0, and for a resonance that the perpendicular wave number must go to infinity. Or if you prefer, and perp square must go to infinity, which is the same thing. This doesn't look like a properly drawn symbol, so let me try again. Okay. I don't know if that's better or worse, but that's perpendicular. Okay. So that's the basis for our discussion. And a couple more things. We're kind of going to ignore a lot of things, but we're going to keep in mind that the toroidal field is proportional to 1 over r. We're going to assume that we are looking at a plasma that looks sort of like this, where we have only one coordinate we really care about, which is the x coordinate. Of course, here we have phi. Let me maybe use a different color for this, just for clarity or to further confuse you, whichever occurs first. That's not where it's supposed to be. It's supposed to go around that phi. This is not to scale, of course, but just to. What happened here? My phi disappeared. Okay. This is phi and this is z. This is big R. Now, this point correspond to x equal a, where a is the minor radius of the plasma. And this is where the wave enters the plasma. And let's assume that we want our resonance to be on axis, that is for x equals 0. And again, we need the wave to make it all the way from x equals a to x equals 0. That is, we need n perp of x to be greater than 0 but finite. And this needs to be true from the edge to the region where we want the absorption to occur. And as I said, we can, for simplicity, say that that's going to be at the on axis. Okay. So that's our setting up of the problem. That was fast, right? As I've already mentioned, there is a lot that we cannot discuss. What we can gather even just intuitively without doing too much math is that the wave will need to have to be set up so that it drives the motion of charged particles in one specific direction. And that can be accomplished by, let's see if I have type of axis that I need. Well, this is going to work. If here I have a parallel and here I have the norm of the electric field, it's going to have to look something like this. That is going to have a profile that is asymmetric in K space, in Fourier space. If I had a symmetric profile, then I would be pushing particles in both directions. There will be a deposition of energy, but not of momentum. This way, there is going to be a deposition of momentum. That's our first consideration. For LHCD, lower hybrid current drive, we need, let's see, what did I use for cyclotron frequencies? Okay, I used a generic, so let me use capital omega now, just for convenience. And let me use my blue pen. Typically, what is going to work is the following: that omega must be between the ion and the electron cyclotron frequencies. But these are the cyclotron frequencies, 1 and 2. Okay. There is not going to be cyclotron damping, but for L equals 0 in the resonance condition I wrote earlier, which I may want to square, I can have Landau damping. Oh, I don't think I've said it out loud. V is the particle velocity, not the fluid velocity. So this is looking at the distribution function of either ions or electrons or both. In this case, it's going to be electrons. So it turns out that the electrons that are going to be absorbing the energy coming from the wave have a velocity that's about 3 times the thermal velocity. And that's where the peak of the energy deposition is going to be. Now, let's look at our dispersion relation. This is something that we know how to derive, and I'm not going to write it to write all the steps. I'm just going to tell you what the various terms look like. But our dielectric tensor is going to have this form. It's going to have a k perp minus I k sub a, I k sub a, k perp, and k parallel with zeros here. And I take the determinant so it's equal to 0. Okay, that's the easy part. Now, k perp is equal to 1 minus the sum over j of omega plasma. Let me use I, not j. My j's are always a challenge. Omega plasma of the particle, of the species, over omega square minus omega cyclotron square. And let's see, I can make everything fit here. I don't need to zoom in to make everything fit. Easier to do it if I don't, actually. The k sub a term is sum over I of omega cyclotron over omega times omega plasma over omega minus omega cyclotron with all the squares of the k's. And finally, the k parallel per term is 1 minus the sum omega plasma over omega square. At least some pieces of this should look familiar. Okay, and Sorry. What did I write? It's not the determinant of this is equal to 0. We need the other piece, the n cross c. Okay, so what we need is the determinant. Let me just write it as well. It's not an hat, so put a vector sign on it. N cross E1 plus K dot E1 equals 0. Now, both n perp and then parallel are non-zero here. This mode is a combination of ordinary and extraordinary modes. So if I write my dispersion relation leaving the most general n, I'm going to get this monster here. Let me just write it. Okay, n parallel square minus k perp. Here I only have IKA. Here I have minus n perp and parallel. Then minus IKA and perp square plus n parallel square minus k perp 0 and perp square minus k parallel 0 and symmetrical and perp and parallel. And I take the determinant of this thing, and these are really set equal to 0. Okay, and you can work this out, but this is going to give me the following equation, right? And perp to the a times, it's a quadratic equation in perp square. So this is an n to the 4th plus b and perp square plus c equals 0, where a is just k perp, b is k perp plus k parallel times n parallel square minus k perp plus ka square. And the last one, c is k parallel n parallel square minus k perp all square minus ka square. Okay, so this is the dispersion relation. And as you can see, this is going to give me n perp, or n perp square if you like, as a function of n parallel. So that's the idea. Okay, now I did mention that the parallel for the electrons that are involved in the lower hybrid current drive is going to be of order of 3 times the thermal velocity of the electrons. That is, they're not at the peak of the dispersion relation, they're actually sort of in the tail, which means that the transfer of energy from the wave to the plasma, well, of course, will increase the energy of those electrons, make them move at higher speeds, and then collisions will try to bring the distribution function back to a Maxwellian, which in turn means that in order to keep the current running, I need to keep my heating, my lower hybrid wave on. It's not once per shot, a once per shot deal. I need to keep the heating running, the wave running. And the other point to notice is that a Coulomb collision, well, the Coulomb collision frequency scales as 1 over v cubed, but these electrons have high velocity. In other words, they are going to be less collisional than the main part of the distribution function of the electrons, and as a result, the dissipation is going to be actually less than you may naively expect, which in turn means you need less power than a first calculation may indicate to keep the current running. But that's some good news for the efficiency of the current drive. And we're not going to get much deeper than this, but this is one piece of the story that we can see from what we already know from sort of the single particle picture. Okay, remember that in these expressions, I'm going to want 10 parallel to be non-zero, or I wouldn't get any resonance. I should mention that the efficiency of the current drive is pretty low at the end, but this is still the best, the most efficient method that we have for driving current, except for bootstrap current, which is something else that we cannot discuss in this course. Okay, time is flying. I want to be able to tell you something more. Let me indicate what the scalings are in this calculation. We're going to use the fact that the ratio between the electron and ion mass is small. Everybody will agree that that's okay, not making any wild assumptions. But this is much less than 1. And then I'm going to use the following scalings, which I'm just going to state without proof, or we'll never get anywhere. So the ratio between the plasma frequency, the cyclotron frequency is order 1 for the electrons. The omega is of the order of omega plasma ions. Well, omega plasma ions over try to make this a little more straight. Over omega ions is of order of omega over omega ions, which is the order of omega cyclotron electrons over omega wave frequency, order and perp, and this is going to be large. Okay, then if I make these assumptions, I can obtain a scaling for my three terms, K perp, K A, and K parallel. In particular, K perp, which is 1 minus, sorry, to make write the electrons first, 1 omega plasma electron square over omega cyclotron electron square minus omega plasma ion square over omega omega square. This of order 1. K sub A is omega plasma electrons over omega times omega cyclotron electrons. So this is going to be large. And K parallel is going to be equal to minus omega plasma electron square over omega square. And this is even larger. Okay, then if I do that, work out things, I obtain that n perp is going to be equal to minus K parallel over 2K perp times n parallel square minus K perp. Let me do it this way. Plus Ka square over K parallel plus or minus. It's going to be easier if I write this as power. Okay, n parallel square minus K perp. Please try to do this calculation. I'm just writing results because we have very little time, but this you can definitely do. So this is B square, and this 4AC, which is 4K perp K A square divided by K parallel. These are under square root, so to the 1/2. Oof. Now, the interesting root is the one with the positive sign. So we're going to get the plus sign. this is going to give me larger n perp square, which correspond to the smaller value of omega over k perp. And that is the reason why the lower hybrid wave is also known as the slow wave. Okay, then we need to keep in mind that k parallel is negative. And we look at this thing, so the factor in front is positive. When you look at this, all this mass, we need it to be positive. But we need two things. The quantity under square root needs to be positive, and it's because we want n perp square to be real and positive. And then if that quantity is positive, everything, the whole expression needs also to be positive. So this is going to give us two requirements. One for omega needs to be above a certain critical value, and one for n parallel that again needs to be above a certain critical value. Let me think various ways I could write this, but you work out the math, please do, and you obtain that omega square must be larger than omega lower hybrid square, which is a function of the position. And this is defined as omega plasma ion, which remember is a function of the position itself, divided by one plus omega plasma electrons square, also function of position, over omega e square, which is actually also function of position because the magnetic field depends on position. Okay, now there is going to be a position where there is a wave particle resonance. That's the position where the energy is deposited. And I'm just going to call that position x sub r. And at that position x sub r, I'm going to have to I mean, I'm going to have my wave to be able to reach that position x sub r. So let's assume for now that the position is either given or unknown, or we'll find it. And for the rest of, well, we don't have much time, but I'm just going to ignore the 1/r dependence of the magnetic field, because that change is going to be of order of the order of the ratio between the minor and major radius, which is less than 1. So I can first approximation ignore that term, that correction. Okay, so square root term, we need n parallel square to be larger than k per let me just write it in okay, how do I want to write it? Okay, I can't do the steps. All right, so let me just write it this way. Square root of k perp plus minus ka square over k parallel, which is a positive number, to the 1/2, everything square. This is just the way we we write it. And let's see, let me just do this part, and then we'll have to leave the rest for maybe another semester. Okay, n parallel square must be larger than 1 minus gamma x to the 1/2 plus x to the 1/2, everything square, where x function of position is omega plasma electron square, again function of position, over omega e, which I'm assuming constant. Big Y is, which are not used yet, is omega square over omega e times omega I, and gamma is 1 minus y over y. The function on the right hand side of this expression has a maximum. Can easily figure that out. And that's going to be at x function of xm, x sub m is x to the maximum, is equal to y squared over 1 minus y, which is equivalent to writing omega plasma electrons square of x over omega e square equal to this other little mess, omega square over omega e omega I all square over 1 minus omega square over omega e omega I. Oof. Okay, point being this function has a maximum at some position, well, n parallel square needs to be larger than the maximum. And just making it equal to that maximum will give me a minimum value for n parallel. And parallel square must be larger than n not m. Some critical value of n parallel which is equal, if you untangle the math, to 1 over 1 minus omega squared over omega e omega I. Okay, so that's actually what we wanted to find, a condition for n parallel. We don't have time to do a lot more, but I would like to stress we've only used fluid theory, and we figured out that n parallel must be larger than this expression if we want our wave to be able to propagate up to our resonance point. And there is lots more other things that we need to ensure is that n perp square is also positive for the range of values of x where our wave is propagating. And it turns out that the efficiency, which we're not going to be able to get to, is actually maximized when n parallel square is minimum. So we have two opposing constraints. We want n parallel to be as small as possible for efficiency, but we need it to be at least above this critical value that we obtain skipping a lot of steps in order for the wave to be able to propagate. Okay, let's see. I guess I'm not going to say anything more. Yeah, actually, just one more thing. From this equation, I should have mentioned omega e and omega I are absolute values. You've noticed that I had signs of in an earlier expression. So and parallel is larger than 1. And that's okay, except that that means that I cannot make n perp positive everywhere. It will happen that at the edge, n perp is going to be imaginary at the edge of the plasma. So there is going to be a small cutoff region to where I'm going to have trouble right at the start, And the solution for that is to put the antenna as close as possible to the plasma to reduce, to shorten the region where the wave is decaying. Remember, evanescent doesn't mean that the wave stops. It means that it decays exponentially in space. Okay, I am well aware that this was not very comprehensive and there was a lot of jumping around and not a lot that was proven in detail, but I hope that this will be helpful and useful to you to recognize that fluid theory can, in fact, tell us quite a bit about the real problems in plasma physics. It's not just for textbooks. Thank you for making it this far. I hope you learned many things from this course, and goodbye.